Hey everyone, Keegan here from Curious Engineering, and we are back with the Altera University series, and specifically we're going to be looking at Lab 2 Part 4. And it's going to be an interesting one. In the previous lab we kind of saw how to use the full adder's basic element and just to represent something, or some two numbers together to represent them on LEDs. So we're going to continue to use that, and we're going to ratchet up a little bit. We're going to display that on hex or 7-segment displays, which is going to be a lot easier to read and kind of see in real time. So this is a cool lab. It's really Altera. I think what they're trying to show us is two things. One, they really want us to use what we've already created. So we're going to instantiate our 7-segment displays that we've created to represent digits. We're going to use comparator circuits. We're going to use full adders. And also some of these specialized converting circuits, which they use as circuit A or circuit B. But it's a really interesting one, and it gets a little complex, and that brings us to the second point. Is this one's going to be a little messy, so kind of bear with me through it. But what they are trying to do is, in part 5, we're going to do almost the exact same thing, but in a much more efficient manner. So just kind of prelude to that. Let me jump to the main screen. So here's all the code they're going to be using for this lab. So a decent amount, for a relatively simple task of adding two numbers together. But as you can see, if you spend a little more time and have a better kind of pseudocode or kind of like algorithm in your mind, it's much simpler. So a lot less code to do the same thing. So that's kind of the second point that they're trying to make. But irregardless, it's a pretty interesting lab. So just as a few kind of notes on purpose here, we're not going to represent numbers greater than 19. So that's because when you need to output a 2 on that other hex, on that more significant hex, it kind of complicates things quite a bit. So we're going to represent the numbers from 0 to 19, and we're going to do that with two inputs. So we are going to have two inputs, x and y. I don't know why this is staying up there. Okay, so x and y. Again, each number is going to be a 4-bit number, and then we're going to represent the sum of those on these two hexes, hex 1 and hex 0. We're also going to have hex 5 and hex 3, just so we know what number we're putting up on x and y. So as you can see, switches 7 through 4 is going to be x, switches 3 through 0 is going to be y. We're going to use all our LEDs just so we can see them. The 9th one is I'll talk a little bit more about that one. That's going to be a little more specific. But again, we want to display x on hex 5 and then y on hex 3. Now, hex 9, or LED 9, as I mentioned, we're only going to use that one for a scenario when x or y is greater than 9, because it's going to be like a warning, hey, we might overflow and go into the 20 number or higher, which is going to be something we can't represent with this lab. But anyways, those are all the elements that we're going to be using on the FPGA itself. And let me talk a bit about kind of the easy things. So I did create a schematic for this, just kind of like, it looks a little messy, but it's exactly what they wanted to have us do. So I'm going to talk about the easiest thing first. So let's talk about hex 5 and hex 3. So as you can see, the x input is going to be represented in this light blue, and this green is represented, or this y input is represented in green. So as you can see, they both directly connect to hex, their associated hexes, and that's what I have presented here. So this 7-segment display, we built this in previous labs. All it is, the two parameters it has this, what I'm saying is a C input, and then its output is dot segment. So I will jump to that real quick, just as kind of a reminder. So we built this a few labs ago. Again, all we're trying to say is, like, based on whatever 4-bit input you give it, we want to know what that corresponding digit is on the segment. So that's what we're doing here. We're instantiating what we've already built. Again, we're going to be using the dot named port style representation of instantiating modules, and again, that's just useful to avoid the scenario when you were to potentially misplace, like putting x second and hex 5 first. This is a way of saying, like, hey, for my .c parameter, I want to connect x directly to it, and for my .segment parameter, I want to connect hex 5 directly to it. So cool. So by doing that, that does everything that we needed to do. So we'll do that for hex 5, and then for hex 3, this guy here, we're connecting that by this statement here. So those are some of our instantiations that we're going to do, those easy ones. And then I'm going to jump into the full adder, so this guy here. So as just kind of a recap on what we did last lab. The full adder, this is a 1-bit full adder, and this is a kind of like a format that Altera has created for us, and that is exactly, this circuit here is exactly what's represented by code, is what you're seeing over here. So with a few, we're using our logic operators to do so, and then we're also using conditional statement, which is just saying, hey, which is just saying like, hey, make sure that we have our sum and our carry out selected accordingly. Now, if you remember in the last lab as well, we in order to do a 4-bit number or a larger number, we needed to connect them in series. So that's why we're adding we toggle in a carry in as well, and then by directly implementing what you see here, by managing your carry ins and your carry outs accordingly, from least significant to more significant bits, then then you're able to represent a larger number. So as you can see here, when you do your instantiations of this full adder, you just really need to follow this model and hook them up directly, and just pretend that A is X and B is Y. Okay, one more last thing to touch on that's really important for this lab. As you can see, that when you add two 4-bit numbers, you need to have that carry out to represent that 5th bit, that more significant number. So that's kind of as an example of what I have here. So pretend that we want to add 8 and 8 together. We know that result is going to be 16, and as you can see, the sum is actually all zeros. So that's an important thing to remember, is like, well, how do we manage the remaining sum when we have a 5th bit in there, when we have our carry out bit being a 1, for example. So just as a reminder here, so just keep that in the back of your mind about that 5th bit. Now we jump to the comparator. We're going to use 3 comparators, and just kind of a recap of that comparator module that we've already built. We're again using a conditional operator here, and we're saying that, hey, if this value that comes into this comparator, this compare in, if that number is greater than what I have here, which is a 4-digit binary number of 1001, and that's 9. So if the input is bigger than 9, then this is going to be true. Our compare out is going to be true. But if it's not bigger than 9, it's going to be 0. So basically, I say, hey, if the value is greater than 9, I want you to output a 1. Or if the value is less than or equal to 9, then the value is going to be 0. So what we have, what was requested of us was to have that LED, as I mentioned, LED 9. If we're getting close to potentially overflowing, we want to have kind of some awareness. So that's all that's happening with these 2 comparators. We're connecting the X input and the Y input to a comparator for X and a comparator for Y, and that output, let me jump to the schematic, that output is going to go to a OR gate. Apologies for the representation, this is an AND gate, but I'm just calling it, should be an OR gate. So if either one is greater than 9, I want that LED to be turned on. So that's what you have with these statements here. So for the compare input on this instantiation, we're connecting X, and then the output I'm calling Z0. So that's just a wire connecting that we're going to connect to our OR gate, and then also we're having the Y input going into the comparator and the output being the Z1. So let me jump to that so that makes sense. Or let me jump to this code here real quick. So as you can see, so the LED is going to be turned on if Z0 is 1 or Z1 is 1. So that's how you see that the LED will be on, or logic level high. Okay, so the last comparator, this one's going to be really important in controlling what digits we're going to be outputting on the 2 hexes, specifically these 2 hexes. So if you think about it too, this is going to be a 0, right, when we're when we have a sum of anywhere from 0 to 9. Now what gets a little complicated is why we need this additional circuitry down here. Well, we need all this down here is when we get to the digit 10, or the sum 10 I should say. When we get to 10, we actually need this to go back to a 0, so almost wrap around, and then this to be a 1, right? So, I mean, it doesn't sound too complex, but again, we're going to need some additional circuitry to make it happen. So just keep that one in the back of your mind. So keep that 5th bit and kind of that idea of needing to wrap that hex 0 when we get to larger sums. So let me talk about oh, sorry, this last comparator. So what I'm doing here is I'm actually going to utilize this sum output. Again, it's a 4-bit number, and we're going to say, hey, is that number greater than 9? And based on that, we're going to be using this Z2 to compare or to control a MUX that we have down here. So that brings me to circuit A, which is what you see down here. So let's take a look at what's going on here. So again, circuit A is going to be a bunch of where we're using select case statements. So pretty much all that's happening is we're going to have our sum, so that's going to be connected to the 0 portion of the MUX, and then we're going to feed that also into this circuit A. And all that's doing, all circuit A is doing is saying, when we get to that scenario of 10, 11, 12, 13, 14, or 15, I want you to, instead of putting out that digit exactly, we want you to output a 0, a 1, a 2, so just this portion of these numbers. So you're saying, hey, for a 4-bit 10, for example, don't output a 10, output 0 instead. And then here's 11, don't output 11, I want you to output instead 1. So that's what we're calling, the output will be this R number. So converting 10 into a smaller number. And I don't think I really touched on this kind of notation yet. So this is what's known as, like what I have here is behavioral modeling. So you have this always statement, and it's going to say, hey, for this scenario, whenever you have this parameter, I want you to start and evaluate, whatever statements you have here. In this case, we're using select case. So every time there's an input to our circuit A, go through this process. So, and again, let me just recap select case statements, how they work, real quick in case I haven't. So based on whatever this input is, this input parameter, there's all the different scenarios for that one. So we're going to have our sum. If our sum is 10, which you see here is a 4-digit binary number, 1010. So that's one case, and then when you list out all your other cases, so we want to do 10 through 15. And once you have all those cases out there, now we want to define what do we want to output. So our output is going to be equal to 4-digit binary 0 in this case. So if that's the if that's the input, the output is going to be a 0. So that's kind of what this case statement is saying. Now you might be asking yourself, Keegan, why do we only do 10 through 15? Well, if you think about a 4-bit binary number, you can only, if you have a 1111, that number is 15. You can't represent a larger number than 15 with only 4 bits. So that's why we have these only up to 15, and that's why we're going to need circuit B to represent those larger numbers of 16, 17, 18, and 19. But I'll jump to that. I'll talk about that next. So as an example, let's talk about, for example, if we want to sum 10 and 2, we know the result's going to be 12. Sorry, just checking my notes real quick. Okay, so we know that number is going to be 12. And as you can see here, if we sum those numbers together, just make sure, just a basic kind of addition, making sure everybody's on the same page. You're going to carry a 1 to this 3rd bit. We're going to bring it down, and then you're going to have the 4th bit. So that number, as you can see, is 12 as well. So in that case, so the sum is going to be 12. So that sum is being connected to here, and also through our circuit A. But you see also that the sum goes to this comparator, and we know if the number is greater than 9, which it is, then this z2 is going to be logic level 1, so it's not going to output the sum, but instead it's going to select whatever is coming out of our circuit A. So if this is high, then the MUX is going to choose this input, and as you remember, instead of carrying the sum through, instead of it being a 10, it's now going to be a 0. And such and such. So that's how this circuit A is working, and in combination with this MUX and comparator. So it's kind of clever little way of doing it. But again, you saw in a previous lab that's what we needed to do to represent a larger number than 9. Okay, circuit B, if I can click on it. Okay, so circuit B is here. So that's an in-series operation to circuit A. And as I mentioned, since we have a 4-bit number that can only represent the numbers 0 through 15, we need to do something a little bit extra. And we're going to use another MUX. And on one side, we're going to take whatever our output from this first MUX is on the 0 portion. And then we're also going to convert whatever that value is in circuit B. So again, we're going to use some behavioral modeling. We're going to use a case statement. And there's going to be 4 cases. So that number, say that, alright, let me walk through this example. Okay, so let's take a look at if we have like a small number, something less than 9 and something less than 15. And then we're going to look at another example where you have a sum that's greater than 9 and also greater than 15, because you need that 5th bit to do so. So those are the 2 examples I'm going to walk through. But the first one, we're going to add 3 and 1. We know that result is going to be 4. So if we see that, so our carryout is a 0, right? So that's going to be selecting whatever input is on this line. And our sum is going to be 4, right? So that's going to be less than 9. So that's going to choose this input. So whatever is going to be, it's going to be output to this t here. And since we know there's no carry out, because that's the select on this next MUX, it's going to just carry through to the next one. So 4 is going to be output on our hex, let me jump to here, hex 0, which is what we want, right? That's going to be just the number 4. We don't want anything crazy to happen there. Now let's look at this other example. If we're going to add 10 and 8, that's going to be 18. As mentioned, it's going to be greater than 9, so that's going to select this result on this MUX. As you can see, the sum is actually going to be 0, 0, 1, 0. So the sum is going to go through circuit A, and that is going to get converted. So if it's 0, 0, 1, 0. Oh, let me step back. I'm sorry. So if you see here, the sum is actually, the sum bits, that number is actually a 2, right? So that's less than 9. So this is gonna choose whatever is on this sum line. It's not gonna go through circuit A. It's gonna be just whatever is represented on the sum line. So that's gonna come out to this t. So we're gonna have a 0, 0, 1, 0 on t. But instead of it passing through, it's gonna also go through circuit B. And if we look at the carryout, that carryout is logic level 1. So that's going to select the output of circuit B as opposed to just going 0, 0, 1, 0 or 2, because that's not what we want. We don't want to output on the hex at 2. We want to output in 18, right? Because 10 plus 8 is 18. We want to output an 8 as opposed to a 2. So that's what circuit B is doing. So circuit B is going to be, let's take a look at that. So yeah, 0, 0, 1, 0 is going to instead be represented by an 8. And that's all this is saying, is that, hey, for this scenario of 0, 1, 2, or 3, I want you to not output that. Instead, I want you to output a 6, a 7, an 8, or a 9. So that's going to do exactly what we needed to do. So as you can see, the carryout is going to select the output of the circuit B. In this case, it's a 2, right? So instead of a 2, we're outputting an 8. And that is what's going to go to our hex. So that's what circuit B is doing. Okay, anything else I want to touch on here? Oh yeah, and then as you can see, instantiations. I just needed to use a bunch of different wires. So the instantiation for circuit B, the input is going to be this T, right? And the output is going to be this U that we're going to connect to our MUX. Alright, so the last thing I think I really need to talk about, or want to talk about, is hex 0 and hex 1. More specifically, what's going on at hex 1. We talked a lot about what's going on with hex 0 with circuit A and circuit B, but hex 1, we only need to represent two different digits on that. We need to represent a 0 for when the value is less than 9, or it needs to be a 1 when the number is greater than 9, right? So the way we're going to accomplish that is we're going to use the comparator from the sum, and we're also going to use this carry out. And those two elements are going to be connected to this MUX. So as you can see, the carry out is connected to the 1 portion of the MUX, and the compare output is connected to the 0 portion of the MUX, as well as the carry out is also connected to, as the selector of the MUX. So I'm going to walk through two examples here. Let's look at what we've already done before. Let's see the number of 3 plus 1 is 4, so we know the sum is going to be actually less than 9, right? So this is going to be a 0 output. So 0 output is being connected to the 0 portion of the MUX, and we know that the carry out is also low, so that's going to get selected as 0. So perfect. It's going to output on the hex exactly what we want it to. Now let's take a look at a number that's both greater than 9 and also greater than 15. So let's, as we saw, 10 plus 8 is going to be 18. So our carry out is going to be logic level 1. So that's going to select the 1 portion of the MUX. And then we see here that the sum is actually less than 9. So this comparator is going to fail, right? So it's going to be a 0, which is good. We don't really care what's there, but since we connected the carry out both to our selector pin as well as this 1 portion, this is actually going to output a 1. So pretty cool. So let's take another example. I guess the third example I don't have presented here would be, let's look at 15 for example. So say y is 5. So the number 15, the carry out is going to be a 0, and then it's going to be a 1, 1, 1, 1, right? The max a 4-bit number can support. So in that case, the comparator is going to be a 1, right? So this is going to be a 1, and the carry out is going to be a 0. So it's going to select this 1. And it's also going to continue to output a 1. So we've gone through each scenario, right? Less than 9, greater than 9, but less than 16, as well as anything greater than 16. So this is going to do exactly what we wanted to do to output a 0 or 1 on that hex. Great, so I think we've done quite a bit of background on this. Again, I'll present all the code if you need it on my GitHub. But again, I recommend you do your best to struggle through it, and then if you need additional help, then go to that resource. Alright, so I think the last thing to do, just checking my notes, we're gonna just build this all together, so let's do it. Okay, so we have, let's minimize just everything all at once. Okay, so let's open up our course prime. Let's do a new project, and I noticed actually there's a version 17.0, and I didn't do a installation or getting up and running movie, so I will do that since I'm gonna have to update this anyways. So anyways, just to look to see that. So I already just kind of ran this to make sure that it works. I'm gonna create a new folder, lab 2 part 4. I want to use that folder. Let me just copy that real quick. Name of the project, everything. So we've done this quite a bit. Feel free to fast forward if you need to. But again, if not, I'm gonna continue to do it here. So feel free to stick around. Right now, we got to make sure I have the correct device. So you can either look at that directly on your chip, or you can. I think it's in some of the documentation as well. So just make sure you have your correct device, the whole thing in the whole number in full. We're not going to be using any specific tools, and let's create this. Alright, again, let's usually pops up in this mode, so if you are adding files, make sure you want to make this selection in your project navigator. we're going to create a new file. We're going to have a Verilog file, and then we're just going to copy and paste what we have, or what we've written. Okay, so once it's in there, let's make sure we save it first. Save it, make sure it's the same name as your top level module here, as well as what you have in the title, or as the title for the lab. So in this case, Lab 2, Part 4. Last thing we need to do, again, we need to do our assignments to all our pins. So let's do that. Again, let's use our tickle commands to do so. Again, you can see all the locations and assignments to each of the pin primitives. And we're going to do that for all our switches, LEDs, and our hexes. Let's go to our tickle console where we're going to input this. Again, if you don't see that, make sure you go to View, Utility, Windows, Tickle Console. And then I'm just going to copy and paste them all in. As you can see, they get automatically assigned, just like we want them to. Okay, so we have our source file, and we have our assignments. So let's go ahead and compile, and I will fast forward because this is very boring otherwise. Okay, all done. Looks like we have just a few warnings. Let's double check them real quick. Nothing too concerning. So let's continue on. Yeah, again, I don't think I really talk about this much. It's always good to kind of look at your summary of what's happened, like how much of your board, or of your chip, I should say, are you actually using, how many pins are you using. But again, for anything that we're doing with these labs, it's going to be well within the capabilities of the chip / board. Excellent. So let's go ahead and program. You can go to Programmer here, or you can go to your Tools. You can go to Programmer here if you don't have it. First thing we always want to do is make sure you have your hardware. You see your hardware there. If you don't have anything there, just make sure it's connected. Or if you might need to install some firmware beforehand. So if you see it there, we're going to detect it. Make sure you choose the correct one. Again, that's going to be on your chip, or it's going to be in some of your documentation. We obviously want to target that, so we're going to add our output file. It's a .sof file. Once it's compiled correctly, that will be presented in your output files. We're going to let it load. So this is the one we care about. We don't care about this empty one. And then let's go ahead and program. And again, you'll see in the upper portion of your screen. Alright, so let's go ahead and test it and make sure everything's working correctly. So we'll do a couple scenarios. We'll do one that's less than 9. Let's do one that's greater than 9 but less than 16. And then let's also do one that's greater than 16 and make sure that our adding circuit is doing what we want it to do. So you'll see it pop up on your upper screen, and I'm just going to talk through it here. So let's represent, let's add 3 plus 6. So I'm going to represent 3 on our Y input, and then let's add 6 together. Again, we get 9. Perfect. It's doing exactly what we want. Now let's represent 15. So let's add 8 and 7, and that gives us 15. Perfect. Now we want to represent a number larger than that. let's do 18, and then we're going to see the input of, or the toggle of the carry in. So let's do 10 on our X input, and then let's do 8 on our Y input. Fantastic. We see 18, and then let's toggle that last one to see 19. Excellent. So the carry in, if we carry in just to add one more, we see our 19. Okay. So one thing to note too is when we're adding those, when we have a value greater than 9 on one of our inputs, the hexes, let me jump to that, just to kind of help explain that. My current design, obviously we can't represent a 10, which is what I had here. It actually represented an 8, so it was kind of like in a failure scenario. So every portion of the 7-segment display was on. That might be something interesting to try if you have a little extra time, is actually have have maybe hex 4 and hex 2 to represent x and y, because when they do get larger than 9, this will behave differently, which is kind of what you saw. Okay, anyways, that's it for this lab. I know it was kind of a lot. It was a little bit messy too, as you can see with some of the circuitry. But look to the next lab. It's going to streamline everything. It's going to be a much smoother implementation. And again, just going to prove Altera's point of spend some time up front and really think through your pseudocode. Okay, so anyways, without further ado, I guess have a good night, everyone, and then we'll see you in the next video. All right, take care.